everyone. Myself Ankita, Faculty Department of IT, AKGEC. Today I'm going to discuss the topic designing a learning system, which is the topic from Unit 1 MLT course PCS 055. So I'll start with introduction, then I will defining what is learning, then we will discuss how to define a learning problem, and then we will try to understand how we can design a generic learning system. So let's start with comparing your traditional programming with machine learning. So when we talk about programming, a purpose of using computers was to solve a problems. For that, we use programming. In that, we provided the computer with the data and the logic to solve that data. The program is just a logic that will solve the information in the data and will give you the output. That was your traditional programming, where we feed the data as well as logic to the computer, and the computer, by using that logic, will manipulate the data to give you the result. But as our time progresses, we want our computers to learn the logic on its own. So we have lots of data available now. So we want a computer to learn the information or the logic from the data. So we are providing the output as well from our previous data, and then the computer is able to generate the program. The program is nothing but the logic of how we can compute output from the data, right? So from the past data, the computer is able to learn the logic of developing the output, and after that it will be able to predict the output for your future data. So basically, what is learning? A computer program is set to learn from experience E with respect to some class of task T and performance measure P. So there is these three terms: experience, task, and performance measure. So a computer program, if it improves the performance measure, which is depicted by P, within experience E, we can say a computer program is learning. So we want our computer program performance to increase over time with the experience. So as we are providing more and more data to our computers, we want it to learn on more and more and improve its performance measure. For example, we will take a very simple example of a computer program that learns to play checkers. So what could be its performance measure? It will involve player checker games it will involve the number of games it has won. Okay, that will be the performance measure. So that is called learning. If a person or a computer is able to improve its performance with an experience, we call it as learning. So whenever we try to solve a problem, we have to define that problem. So for defining the problem, these are the three aspects. First, we have to define the task. What task we want our program to learn. Second is the performance measure. How we are able to assess that it's learning. It's by checking the performance measure. So if the number of games that is won against opponent has increased, the percentage of games that has increased, then we can say it has learned. And the training experience is nothing but the data. It can play a practice games against itself and gather the data and improve itself. So with this, we are able to define your machine learning. So a computer program which learns from experience is called as machine learning program or simply learning program. So if a computer is able to learn means it's able to improve its performance measure, we can say it is learning. So Arthur Samuel has coined the term machine learning, and it has defined the machine learning as a field of study that gives the ability to the computers to learn without being explicitly programmed. So we are not assisting the computers to learn at every step. Instead, we want it to learn on its own. So with this, we have a comprehensive definition of machine learning. That is, it is defined as a discipline of AI that provide machines to the ability to automatically learn from the data and past experiences to identify patterns. So first, it observes the data, and with that data, it is able to identify the patterns, and then when it has learned something substantial, it can make predictions. And that's all without human intervention. That's the beauty of your machine learning, that we don't require human to help the computers to learn the logic. The computer will learn the logic, as well as the computer will improve its performance over time with more and more data coming. So whenever we want to design such a learning system, we have some generic steps. So when we feed a machine learning algorithm some input data, it will try to make the logic by making your logical models. So it will try to build mathematicals or logical models so that it is able to learn the logic behind this data. And then when the new data is fed into the models, we are able to predict the output. So here the purpose of learning system is to predict the output based on whatever logical models it has built. So you can say this model is just a way to learn the patterns, to learn the logic behind the data. So once we have learned the logic, once we have find out the connection between the input and output, we are able to predict the output for the new data. So these are 5 steps by which we can design a learning system. First is the choosing training experience. It means that what data we are going to feed to the system so that it can learn from it. That's a very important thing because it's a basis of what it has learning. So if my data is wrong, if my data is faulty, if my data is not relevant, then obviously my learning will be incomplete. Then I have to choose the target function. Now this target function is nothing but the logic. So how we are going to represent the input is converting to output, and then how we can represent the target function, and then what is the best algorithm by which you can realize this target function, and finally we have the design phase. Now when we talk about training experience, it is very important because it has significant impact on the success and the failure of the learner. So in this we have 3 major attributes. First is the training experience providing direct or indirect feedback. That is, whatever data that we are feeding to the system, is it giving me the direct feedback or the indirect feedback? Second is the degree to which learner controls the sequence of these training examples. So we have giving some training examples, and in what order these learner should be able to learn this, and then how we are able to represent the distribution of examples over which the final system performance must be measured. Now with these 3 points, I will be explaining them one by one. The first is whether the training experience provide direct or indirect feedback. So for explaining this process, we will like to take an example of checkers game, right? So in checkers game, we have a 16 by 16 board. It is just similar to as that of a chess. And then we try to have 2 types of pawns, red color pawns or black color pawns, and they have to, reach the opponent side, okay, by you can say killing the opponent. So it has this, suppose it has to use a find. So if it reach the opponent side, it will become the king. Otherwise, the only way it can move is only diagonally. So this is a just brief description. So once it after killing this piece, it can move. It can finally reach to this position, and then if once it reaches this position, it will become the king, right? So this is just a brief description how we play checkers game, and we are trying to construct a machine learning program is able to play checkers, right? So when you are talking about direct training example, it consists of individual checkerboard states and correct move for each. Now this is a checkerboard state, right? The position of all the pieces are present. That is a checkerboard state. And if suppose I am at this position, it will also, in direct training examples, I will be having correct move at for each checkerboard state. Suppose this is my current state, I will be having the best move for this piece in my direct training examples. It is like that we have a trainer with me and I'm trying to learn from that trainer. So at each step, the trainer will tell me now this is the best move to play. Okay, so that is your direct training examples. We have all the board state, and for each board state, I will be having the best move, right? Second is your indirect training examples. In this, it consists of move sequences and final outcomes of the various games played. So it means that in indirect training example, I don't have any trainer. I will have a data which will say that yes, if you move this, now there is a data that in some game, if a person have taken this move, so at the end, the player has lost the game or player has won the game. So we have such indirect training examples. Now the problem here arises that how we can say the ultimate win or ultimate loss of that player after playing this move is having a direct impact. So if it is, maybe it has won the game, so this might not be an optimal move. And when you won a game, it's a combination of moves that you played, right? So maybe the current move that is we are checking, it has no impact on the win or lose position. So we can say we have to use credit assignment, that is this board is position is right or not wrong based on the final outcome. So the problem arises is because the game can be lost even when early moves are optimal if these are followed by later by poor moves. As I said, that the final victory or loss is only dependent upon the combination of moves we have played. But in indirect trading examples, we are only getting the final outcome and the current move, right? So it is not that good, but it is what we generally get in your machine learning algorithms. We don't get this. We don't have trainer to tell at each step that, yeah, this is wrong, this is right. This is possible only for humans, right? So next is degree to which learner control the sequence of training examples. How the training learner is choosing the training examples to learn from, right? So here the learner might depend on the trainer. The trainer is going to select, okay, now this is the best game, you should learn from this game, right? That is the learner oriented. Second is learner may find itself proposed board states and find particularly confusing as the trainer. So it is just a hybrid way in which I will learn on its own, and sometimes when I get stuck, I will ask my learner. Okay. And third is learner may have complete control over both the board states and training classification as it does, and it learns on itself. So it's like, suppose I will give you an example of learning a bicycle, right? So if I have my parent with me, it will tell me the best move every time, right? Yeah, just move the pedal here or move it there, and that's the way you can apply the brakes. So that is, I have the trainer with me every time I move. Second is, I have my trainer, but I will call to him only when I'm stuck to some issues, right? And the third way is, I don't have any trainer. I will do all the learning process on my own. I will take out my cycle and try to learn by my own mistakes. Second, or by my observations that I have done so far. Next is how well the training experience represents the distribution of examples over the final system performance. So here, whenever we are learning, we are using some data, and whenever we are performing, we are using some other data. So the data from which I have learned should be similar to that data, the problems that I'm going to perform. For example, if I have learned my bicycling in the alleys or small gullies, so it will be difficult for me to drive in the highways, right? Because I have learned to drive only in the small gullies where speed is very small, less, right? So therefore, whatever training experience we are giving, we have to ensure that the environment where the program will actually work, we are giving the similar training experience to that program. So that was choosing your training experience. Next step is choosing your target function. Now, in this target function, we are trying to understand what we are going to learn, right? So we have our data available to us. Now we want to understand what we want to learn. So when we want to understand in the checkers game, what should we learn? We have to generate the best move every time. So here the program only need to choose the best move. Why the best move? Why? Because with the combination of best moves, you are guaranteed that you will win the game. So here the program has to learn to choose the best move. So we can represent it as choose move B to M, where B is the board state and this is the valid moves, a set of valid moves. So I have a set of board states and I have a set of valid moves, and I have to choose the best move, the most optimal move from these valid moves, right? So I have a board state, I have valid moves, and I have to choose the best move of all the possible moves. Now, choose moves function will turn out to be very difficult to learn given the kind of indirect training experience we have. So you can say, if I have indirect training experience, how will I be able to understand, okay, which is my best move? There are, suppose, 5 legal moves possible. In checkers game, we only have 4 legal moves, right? only 2 legal moves. So out of these 2 legal moves, I have to choose the optimal move. Now it is very difficult for me to decide which is my best move if I have the indirect terrain experience where I only have the final. Suppose this is my, I will make a simplified game. I have my, suppose, I have my piece over here. The valid move is I can move over here or I can move over here. Okay. So my training experience told me that if you move over here, you might win the game, and if you move here, you might lose the game, because in some other game, a person has chosen this move and he has won the game. And if in some other game, if a person has chosen this game, he has ultimately lost the game. Now again, as we have discussed, it is not, we not get cleared that whether this move is optimal or not. Why? Maybe this is the best move, but at later stages, the program has given very poor moves, at the result of which it has lost, right? So how we are going to decide? For that, first is I have to assign use a evaluation function to assign a numerical value to each board state. So the purpose is, and I want to assign a board state a numerical value, right? Now this numerical value, now this is target function which will compute numerical value for each of the board state. So how we are going to calculate this value v, that is target function v. Now for that, we have to keep in mind that we have to give higher scores to better board states. The board state which are better in position, we will give them higher points. Now our purpose will be to move to a board state which have higher points. Okay. So for example, if the B is a final board state and beta has 1, the value of BB will be 100. If the B is a final board state and it has lost, the value of BB will be minus 100. If the result is drawn, the value of BB will be 0. And if the B is not a final state, the value will be BB dash. Now what is BB dash? Okay, so BB dash, we have to search all the way to the end of the game. That is right. So we have to understand, enemy it has lost, this is a lesser way, and if it has 1, it will be assigned 100. Okay. So obviously, we have discussed earlier also, it is a non-operational way. It's good in theory, but it's very difficult to find out the scores in such a way. Next is how we can represent that target function. Now, my target function is to assign a numeric value to every board position. So, how we are going to find out that numeric value? Now, either I can use a big table in which I will have all board positions and I will assign by hand what is the value to it. Now, it's very not practical because we have many millions of board states. It's not possible for me. Rules, I can use rules, right? Like if I have a condition, like if a board position has more kings, you can assign it more higher value. Again, it is difficult. Then I can assume a polynomial function using a math formula, or I can use the neural network. So for neural network to work for this situation, we have to have lot of data, which is not always present for us. So we can use here polynomial function. Now for polynomial function, this is only one way by which I can represent my target function. Now the purpose of this formula is to assign a numeric value to a board position, right? For that, I have made a formula, a linear equation in which I have W naught. Now this W represents the weights. Now this weight we need to learn by experience, right? And this x1, x2, x3, x4, xy are the x1 represent number of black pieces, number of red pieces, x3 is number of black kings, x4 is number of red kings, x5 is the number of black pieces is in danger, and x6 is the number of red pieces in danger. So by the weighted numbers of these, by assigning these weights, we are able to find out the VB, that is approximate real world value of a board state. Okay, so with this, this is my situation right now. I know my task is to play checkers. My performance measure is a percent of games won in the world tournament. And experience is that playing against itself. Target function is that we are mapping the V to a real value. And again, I am representing my target function as a weighted sums of the various factors. Now, how we are going to assign numbers using this, how we are going to learn these weights. Okay, so for that I have to use my training examples. Now for training examples, I have to have this vtrain value for each of the training examples I have. I only have, I only have games with me. Okay, I have a game trail with me. Okay, this move, suppose this is my way, and I deal with this move and then this move and then this move. Ultimately, you have won the game. Yes, it has won the game. Or I have the knowledge like this is my board position. My pawn is over here and it is moving like this, and ultimately it has lost the game. So we have this information with us as training examples, right? Now I have to assign them a vtrain value so that my system is able to learn that. Okay, so how it will go? If the black has already won and x2 is 0, and there is no red pieces left, so my vtrain will be 100. Okay, so x1 is 3, x2 is 0, x3 is 1, x3 is the number of black kings, x4 is 0, x5 is 0, and xx is 0, and I have given the value as plus 100. So the function approximation procedure will be described as deriving training examples from indirect training experience available to the learner. Okay, so training examples we will derive from all the games we have so far. We will assign this vtrain value to it, and then we'll try to adjust the weight wi to best fit this training examples. So if I have the games, I have the training examples. Now I have to find out the wi. So how we are going to find the wi? Now we can assume that the value of a board position B, train B, is dependent on the successor. Okay, successor means suppose that I have a board state. My state is my current pawn is over here. Okay, now next would I said I will move this way. So next state is this. Again, next state is this. Now suppose this is your winning position. All right. So my vtrain at this position B is dependent on its successor. Fine. Now this is successor. Now the vtrain value of B dash is dependent upon this one, its successor. Okay. Suppose V double dash. Now we know at V double dash this is 1. We have won the game. So what happens? We are just bootstrapping the process. So if it is 1, we'll assign it 100 points. Then its VB is dependent upon this. We will assign 100 points or 80 points. With this, I will assign some points. So we'll address the weights so as to fit the training example. Right? So value of vtrain B is dependent upon the successor values, and ultimately, if we compute the successor from the subsequent moves, we will reach the end game, whether the person has lose the game or won the game. Right? So with that, I can adjust my weights on the basis of that. Okay. Now, when I'm trying to adjust the weight, I have to use the formula vtrain B minus V2. Whatever value I am getting, whatever value the training example have. With this training example, I have some value, and this is the value that is vtrain B is the value of a board state in a training example. V cap B is the value of my evaluation function, that is, or you can say target function of my game that I'm currently playing. So I will try to minimize the errors of these two by squaring them, and by this I will try to adjust my weights to understand I will try to improve the weights, right? So this is how we are going to update the weight with this formula. This is how the weight is dependent upon the neta. Neta is your learning rate, and vtrain and B dash B multiplied by xy. Okay? Xi is the number of feature value. Now at the end we'll have this final design. We will have experiment generator, which will create the new problem. We will have performance system, which will actually play the game. Then we have the critique, which will be using training examples from the generalizer to give you the rating. Now, performance system is the module that must solve the given performance task by using the learn target function. So, performance system is a module that will actually solve the problem. Critique will try to improve your program. Generalizer takes the input as the training examples and produce an output hypothesis, whereas experiment generator will take the input from the current hypothesis and output the new problem. Now, this is the sequence of which I have used. First is we will try to determine the training experience. I have used the game against itself, that is indirect learning experience. Then I have used determine the representation of learn function as the linear function of 6 features. And then I have used the gradient descent, that is I have tried to minimize the error delta I by using the gradient descent to find the complete design. So thank you. This is for how we have discussed how we can design a generic learning system.